Okay, hello everybody. Welcome to this not very typical talk that we'll have today. Karsten was working in MAGIC, in the MAGIC International Collaboration during several years, and in particular, he was a postdoc working here at the IAC for MAGIC, and at some moment he decided just to move from science into industry, and now he's going to tell us about his experience and things that we can learn from what we are doing, and we can learn
from each other.
So thanks, Karsten, for visiting us again. Okay.
Thank you for the introduction. Lo siento, mi español es muy mal. Voy a presentar todo en inglés. I hope that's fine for you. I can order food, but I don't think I can give this presentation in Spanish. Yeah, the title says that looks like I'm gonna talk only about my life, but that's of course not true. I'm going to try to focus on what we can learn from each other and how we can collaborate, and yeah, hopefully do more work together in the future. So, what am I going to talk about? I'm going to make a short introduction into what I did as a scientist, but really briefly, top level, not too much into the details, just to help everybody understand what I was taking from my work as a scientist into work in industry. Part of that is now also an introduction to functional safety, and then I will go to this connection between science and industry. So Ramon has already mentioned that I was a postdoc here working for the MAGIC telescopes. You can see a very nice picture there on the right from MAGIC 2. I worked in TeV gamma rays on a variety of different sources, from AGNs to pulsar wind nebula to novae or smell. So if you have questions about this, you can also approach me, but I'm not going to talk about this now. I worked in two large collaborations, MAGIC and also Veritas in the United States. And of course, I had a lot of collaborations over the entire electromagnetic spectrum, using as well X-ray instruments, radio telescopes, optical telescopes, and so on. And life as an astronomer, of course, brought me through too many places. I worked in Croatia, in Germany, in Finland, in Spain, and the US, and of course traveled to many more places than that. But what is actually the real day-to-day work? Well, when we think about it, a lot what we are doing, what I'm pretty sure lots of people are doing here in this room, is data analysis. We collect data, we collect tons of data, and we try to reduce the data, we try to understand the data, we have to do noise reduction, all these kind of things, and eventually we want to filter out the physics that we do. So in my case, the long-term goal was of course to determine the origin of cosmic rays. I wanted to understand how sources in the cosmos accelerate particles to TeV, even PeV energies, and yeah, understand these processes. I brought a little video. These are some of the events we recorded in MAGIC 1. And something that fascinated me from the very beginning is that a lot of what we do in the end is software. I mean, there's the hardware part, obviously. It's very a big challenge to build such a big telescope. But then a lot of it actually is software in the end, and how you analyze the software. And we can learn a lot later on about the experiment and improve the experiment completely. In some cases, you get a completely new instrument, you can do completely new things that you didn't expect. So there are these two parts, no? There's the hardware and the software. And I tried a lot to work also on software development, improving our energy estimation, our image cleaning, our background suppression, noise suppression, and all these things. And this is something that still helps me now actually in my job later on, you will see. Additionally, we work obviously in a large collaboration, so I also had some responsibilities that I had to take, like scheduling the observations that now Peppa is doing, as I heard, like coordinating our publications. As a publication manager, for instance, I was going through all the articles that we were writing in a collaboration, checking for mistakes, giving advice, and trying to streamline the process, trying to help people if they needed anything to complete the applications and so on. So this is a lot of management work, which in the end you also do in a company. I mean, this is not so different from what I'm doing now. I, of course, was leading also observation shifts, teaching people about how to run the telescopes, and was an AGN convener, which means I helped organize the AGN group and Magic, and of course supervising or co-supervising students like master students and PhD students here at the IC. And all of these things actually in one way or another I'm still doing them now in a way. So I left science in November 2014. I was working in the US at the time, and as I discovered also in the United States funding is very difficult, and eventually our group ran out of funding, and I decided that this was basically the last time that I'm going to beg for money and I'm going to go to the industry and try something new. And so I moved back to Germany. I had some contacts there, fortunately, and started to work as a software tester. Like I said, I worked a lot on software, so it was natural to test software. I was not going to go directly into the development of software because I didn't have the expertise in developing software for industry, but I could definitely do tests. And what I didn't mention here on the slide, I went into the automotive industry. Specifically, Audi is the client that the company is working for, so I was testing software from cars. Quickly then I became a test manager. The group was growing, and again coordination and management duties came up, and also, like I mentioned before, it didn't take long and I started supervising a bachelor's thesis. In this case it was about automatizing the testing. We wanted to do as much as possible on the computer, not by hand. So we had somebody work on that in his bachelor's thesis. I decided, or how to say, it happens that I had the opportunity to move to a different company. I actually stayed there only a short time because then yet another company asked me to come there. So in the end, what you can see, you change jobs quite often. Can happen very quickly. And I completely moved to a different field. I moved away from the software testing and I moved to what is called functional safety. And this is a field that is not very well known, but actually it's super important, so I will explain it a bit more. And there I'm currently supervising 2 PhD students actually. So what is functional safety? I put here the nice picture with the car. This is something that we don't want to happen. Everybody's nightmare basically. So we have to keep in mind that any system that we design will have some kind of failures eventually. I mean, we try to make the car perfect, but it's unrealistic to believe that it will never fail. And the job of a functional safety manager is to analyze these failures, these probabilities that failures happen, and tries to reduce them to an acceptable risk, I mean to an acceptable level. And so what do? We do a risk analysis. We check if a piece in the car fails, for instance the brakes. What kind of accidents can happen? How are people injured? How often can it happen, and is the driver able to do something against it? If the brakes fail, I'm pretty sure you cannot do much. So this is a very severe hazard that we have to treat and that we have to do something about, and we have to devise methods to prevent these kind of failures. So what does it mean, acceptable level, acceptable risk? Well, accepted by society. So it means if you buy a new car and you go on the highway and suddenly the brakes fail and you have a very bad accident and lots of people die, I'm sure society will not accept that and they will stop buying these cars. But if after 10 years, for instance, your gears don't work so well anymore and you have problems shifting between the gears or so, people will say, okay, it's an old car, I can get a new one. I mean, I accept that this car has reached the end of life. So these are the trade-offs that we are making. We differentiate between hardware and software failures. Here actually come back the cosmic rays. Because unfortunately cosmic rays of course still bombard us everywhere, and they bombard all the computer chips that we use in the cars. And these create what we call bit flips. So you get a small charge in the chips, and it creates a non-wanted result in the code. So, for instance, it means a device could switch on because suddenly in the software one parameter is set from 0 to 1, and then maybe the brakes turn on even though you don't want it. So, but there are methods to prevent that. For instance, you can double check should the brakes really turn on or not, and so you can have error correction in the software. And we are determining how much work do we have to put in the software, how much of this error correction do we actually have to use, based on how severe the risk and the damage later on will be. And this is important also for another reason, because of course it's always about money. The companies eventually will get sued if an accident happens. So they are trying to reduce also the risk for lawsuits later on. There's an international norm for this, and there's a test that you're taking. So I went to study again for a couple of weeks, and I finally did the test, and I'm now an official functional safety engineer. And this norm provides you with the procedures, with the methods that you apply. What we try is to have full coverage of all the risks that can happen, which is really difficult. I mean, you have the whole car in the end, and there's a lot of things that can happen, right? So you have to be very methodical in analyzing all possible risks and all possible outcomes. And this norm, this international norm, is trying to help you, to give you the procedures and the methods to do exactly that. In the end, we also work very closely with the developers, with the software developers and the hardware developers, and they often ask us, for instance, questions like, how fast can I drive? Because as the speed increases, of course the risk for injury increases. So then I can tell them, well, if you go that fast, the risk is very high that somebody gets killed, so we should consider that, and maybe we should go slower. Things like that. So what are the typical tasks? I said that I analyze risks, so there's a hazard and risk analysis where I really quantify all the risks and all the possible injuries and damages, and how people can react to that. But now my task was actually a very interesting and new one. As you know, we are working to have self-driving cars, and in the case of an autonomous car, a human cannot actually do something about these kind of failures anymore. In some cases the car would be completely empty, it would just be driving around on its own. There's nobody to stop it if for instance you have a self-acceleration for some reason, because the motor decides it wants to accelerate. So this is a new challenge and makes everything a lot more complicated actually. Based on this risk analysis, I devise safety goals like do not exceed 100 kilometers per hour or something like that, and then of course measures how we can reduce the risks to this acceptable level that we want to have. And I said redundancies in the code, it can go so far that you have also redundancies in the brakes, like for instance you have two individual systems of brakes, so that if one system fails you can switch to the other one. That can be a method. Of course it's not enough to just do this analysis and then devise these methods. Measures, we have to be sure that they are implemented and that they are working. So there's a lot of testing involved, a lot of documentation, and at the very end, when everything is proven to work and all these measures have been actually done, I have to put my signature under there. As we often say, signed with blood, that now the car is kind of safe. We document everything, there are reviews and so on. A lot of it is about keeping independence from the developers and from the others. I mean, they're trying to make sure that you are not forced to say, yeah, it's safe, but actually it isn't, because, I mean, it's about money. The company might say, oof, but we need to bring out this product or whatever. So there are measures to also make sure that there are independent checks and that you're not coerced to say the car is safe. So I mentioned that we are going into autonomous driving and that this is a big challenge, and I wanted to mention a bit why. So the people that are building cars, they're machine builders. I mean, there's literally in Germany there is a course at the university, a degree, an engineering degree that is just for building machines. They don't learn anything about computers, about data analysis, about photosensors and so on. They don't know these things. They are used to take parts like the brakes or pieces of the motor and work with those. But already the control software is a challenge for them. And now we are coming and we are saying that from having some small, really tiny controller chips with very little data, just still controlling the brakes, for instance, to a huge amount of data, terabytes of data, lots of sensors in the car. So I put here, this is from the recently launched Audi A8, all the sensors that the car has. It has infrared cameras, it has ultrasound, it has long-range radar and short-range radar actually. It has cameras on the top for the front and the rear. It has lots and lots and lots of sensors and is collecting a lot of data. Of course, you need all the processing power for that and analyze all of that. Personally, I'm working on automated valet parking. This means that in the future you're going to be able to bring your car to a parking garage, leave it at the entrance. Well, you have to pay, of course, and then the car will enter, find its own parking spot, and when you need it, you can call it back. You might even, in the meantime, send it to get a car wash, or you could send it to the post office to collect packages for you and stuff like that. I saw in the proposal that they also want to put champagne in there for the rich people and whatever, but any case, and you can, for instance, go shopping and you come out of the store and you say, I would like the car to be parked in front of the store now so that I can quickly enter with the kids and whatnot, and it will come to you, and then you can enter and you can drive away. Well, like I said, it's a new challenge. This car is going to drive around in a restricted area, but still is going to drive around on its own completely. There's nobody in there who can double check, for instance, where it's going or if it's going too fast and so on. So we have to make sure that this will be safe, because what we don't want is that somebody gets killed, obviously, by this car. It would be a total disaster. So theoretical studies have shown that in principle, to prove that this is safe, you would have to drive something like 6 billion kilometers or so. You have to, in principle, try out all possible measures. It's just completely unfeasible. Now we are thinking about statistical methods that we can use. We're trying to identify really what the critical situations are, and that was part of also what I was working on. And I realized, for many years nobody really managed to attack this problem. Everybody was saying it's so complicated, what can we do? And I said, well, we apply very simple rules from physics. We simplify as much as we can. We build a very simple model that describes reality reasonably well, and then we complicate it more as we move along, and we realize that we need more details. But we start with something very simple, something that we understand and that we can control very well. So we start with very simple basic equations of motion, and we see how fast can we brake, how long is the distance for the brake, and we can calculate what kind of distance do we need to the passengers, to the other parking cars, and so on. And actually it turned out that this is in the end not so difficult, and it helped us a lot to understand where the critical situations are. And yes, of things like ramps, you go down, of course the car accelerates, and you have blind spots and so on. It's all something that we can still handle, more or less. What actually worries me a lot is that there are situations, as I calculated, where you cannot prevent an accident. And these are the situations where, for instance, a child is running in front of a car. So, well, we are working very hard to have the car react even faster than a human being, but you would be surprised that, considering that the car has a lot of computer chips and all the information has to come from the sensors, needs to be analyzed, and then has to be processed in the central processing unit. The decision has to be taken that you want to brake and that there's a human being coming in front of the car. So all of this takes time, and we're working very hard to shorten this time, but at the moment it's not so much faster than what a human being would do. Of course you can react maybe better, more decisively, like braking with 100%, where a human being would maybe not be fast enough to push for 100%, but still we need to improve this. We need to become faster. So I mentioned that I'm supervising 2 PhD students. So there's a collaboration with the local technical university in Ingolstadt. It's called SAFIR, Safety for All Innovative Research Partnership on Global Vehicle and Road Safety Systems. I had to read that, I cannot remember that, I remember SAFIR. And it's funded jointly by the German government and by industry sources. So in total there is something like 7.5 million euros in this project. And there are many partners like BMW, Audi, Continental, producers of sensors and radars and so on, who are participating there. They have a very nice equipment there. For instance, they have a large hall where they can produce rain and have cars drive around under very specific conditions, and you can test really how long does it take to brake, or does it lose contact with the ground and slide around and stuff like that. So they have very good installations. And our company, for instance, participates with 3 PhD students in the whole project. One of them is working on sensor-related issues, and 2 more are working on the safety issues. So I brought as an example how we are kind of struggling the LiDAR example. So a lot of you have probably worked with the LiDAR, or maybe didn't even realize that the data they were using was corrected by data from a LiDAR. So I brought this plot that is from a diploma thesis done in magic by Christian Fruck, who worked hard to understand the LiDAR data that is collected for the magic telescope. And I mean, a LiDAR gives us so much information. It gives us information about the Kalima, for instance. So in the lower height range you see Rayleigh scattering from the aerosols. And then you see some clouds there, and then finally, you get into an uncertainty region. Anyhow, so you get a lot of information about the whole sky. And the car makers, we are now at that level that I was talking to a professor from the local university who said, oh, we just figured out we have a problem, because if it's winter and foggy, or the exhaust fumes from the car in front of you is expanding, that will cause the LiDAR to scatter, and then we don't see the car in front of us anymore, and we don't know the distance. And I said, well, of course it does. I mean, we're using it all the time to measure scattering. So there are people who know very well how this scattering works, and they know very well what kind of frequencies to use and what to learn from the scattering as well, because this is information I told them we can use. We can determine really what are the weather conditions, how fast should we drive, for instance, and how reliable is the data from also other sensors like the cameras and so on. So I think we can do much more with the data that we are now collecting in the cars, but people don't even know about it. And they're reinventing the wheel. They are kind of doing the same learning curve that astrophysicists have been doing many years ago. And this is just one example. It gets worse when it comes to photosensors. I mean, what happens when some pixels break? Does it mean that the results become so unreliable that we cannot use them anymore? How do we calibrate the cameras? The cars have to work in Death Valley at 60 degrees even. They have to work also in the Arctic at -40 or something. So these sensors need to be calibrated for a wide range of extreme temperatures. And I think, again, there's a lot of experience with calibrating sensors here in the room. So that's definitely something that we should use. So in retrospect, what helped my transition, I think I learned a lot about management actually without realizing it, partly here in Magic, but also when I was in the US I took a management course, and it made me realize that all our international collaborations and working together is not so different from a job in the industry. You have lots of meetings, and it's the same in the end. These skills that I developed in machine learning and computing in general, of course, they helped all the data analysis things. There are courses you can take actually if you're interested in that prove that you're a data analyst. I usually, if somebody asks me, just take out my PhD and says my PhD proves that I'm a data analyst, I know how to analyze data. An understanding of statistics, I think, will be very important for almost everything. It's important in medical sciences, it will be important here in the automotive industry. We will always need statistics, and we are always talking about very large numbers now. And then, as I mentioned before, simple concepts of physics are really important. Making a model, using the spherical cow to cover the basics, and then make it more complicated as you go along. So, in conclusion, I think actually in astronomy we already developed a lot of solutions to the problems that the industry is facing now, and I think we should collaborate more and exchange our knowledge. Companies are usually worried about secrets getting out, so you need an NDA, you need some agreements and so on, but it can work. I mean, we've done it before and it can be done, definitely. So this long experience in data analysis, also I didn't fully mention noise reduction, noise cancellation. I mean, that is also a very big issue, and I think it's really important to collaborate on that. Thank you.
Thank you very much for the very nice talk. It was very interesting to see the changes. Questions, comments for Karsten? Okay, let me start. So from your point of view, this collaboration between industry and science here, I mean, in which term would you think it's the best way to do it, apart from the political issues?
Yeah.
Because of course we are not in touch with the reality, let's say, of the cars. Would you like to, take our studies and directly the company will translate it to your field, or would you feel that the two teams should get closer and we should learn about what you are doing more and the company?
Yeah. So I think the companies will at the beginning be reluctant to work directly together and share information. So the first thing would be to understand what has already been done here. And I mean, I know it, I know how much work has been done in photosensors and so on, but also reflective surfaces and so on and so on. We need all of that. So I think the first step is kind of a review of what is already there, what could be interesting for industry, and then come with already some research that has been done and show them, look, we have done all of these things and we think this is interesting for you, and that can spark the collaboration, I think. And then the next step would be really to bring groups together and exchange notes. But first, I mean, I'm the only one who basically realized that information is already there. Even the professors at the local university didn't realize that. So, yeah, I think I want to start doing some awareness, and I'm also trying to do this here, and I'm doing the same at the company too. Yeah.
First of all, thank you very much that you gave this talk about the transition from astronomy to industry. I think almost everybody of us from time to time is asking if we should switch for some reason. So regarding this, I have a question. So which skills did you think or have you acquired during your PhD, but also through postdoc phase, which you think are valuable for the industry? So I'm asking in particular writing applications, so you have to make, of course, a publicity. What do you think, what is important to emphasize?
Yeah, but you mean now in the sense of a CV that you're writing, yes? Yeah. Yeah. So what I learned is, I mean, we focus, when we write a CV in science, we focus very much on all the publications we did and the conferences we attended and all of these things. But a person in the industry will not be interested in that. I mean, you can have a side note, I published 50 papers or something, but they will not be interested in that. They will be more interested in soft skills, like the languages that you acquired, like you speak a lot of languages, that would be definitely a bonus. And the computing skills, like with what operating systems have you worked, what programming languages have you used. Like I mentioned, machine learning is now a buzzword. It took, unbelievably, it just arrived now at Audi that machine learning is a big thing. I went to a talk the other day before I came here, where the CTO for the cybersecurity part of Audi realized that machine learning, machines are becoming so intelligent, this is going to be a big thing. So I mean, they're very slow. So when you come and you tell them, I know computers, I have done this, that's a big thing. But focus more on your skills and rather not so much on your results from science, because they will not understand them and they will get bored. Also, a mistake that people often do is that they often mention hobbies and stuff like that. That is something that doesn't interest them as much. And they, yeah, and it's hard. I mean, I always am being told, oh, I'm so surprised that you're doing this and you're doing such a great work because you didn't study this and you came in, as we say, from the side in Germany, no? So, but it's funny to hear that now I get praised that I'm doing a good job, but then there's this saying, but I didn't expect it, you're not one of us, no? So you have to prove to them that you're able to do something. And an important point is that you get to know the company where you're applying. You should check what they do, what they're really looking for. It's best if you know somebody there, really. That makes a huge difference, because they can tell you, yeah, it's true, it's sad but true, because they can tell you what are the current problems and focuses. So, yeah.
Hello.
Hi.
You mentioned that you are supervising two PhD students, so my question would be like, how hard would it be for you now if you decide to go back to academy, or is it one lifetime thing that if you decide to go to industry you can never go back?
You mean to go to work again at an institute? Well, no, there are actually possibilities. There are people who work part-time at the institute and part-time in the company. So you could do some teaching work and like also the supervising of students and still be in a company. So we have cases of people who do that. So yeah, it's actually a possibility. And in particular, these are usually people who did a PhD and who were working in science, and they want to go back and do some teaching. Yeah, so it's possible, yes. And also these institutes, like the technical university we have in Ingolstadt, they are of course very interested in people to come and teach there. So they also offer a professorship to people who come from industry, who have a scientific background. Yeah, so there are possibilities, yes.
Karsten.
Hi.
Hi. Thank you for the talk. Do you think that in order to increase the collaboration between academia and industry, there is a need of communicating more the results of, for example, new techniques that we develop for the instrumentation area, maybe because we are more focused on the scientific results that we obtain, but I think the new things that we develop or we gain doing new instrumentation are not not much communicated.
Yeah.
Would that help?
Yes. It goes back to the saying, it's the journey, not the destination. I mean, we are very much focused on the results, which, I mean, makes sense because other scientists, they want to discuss the results with you. They don't necessarily want to discuss the instrumentation. But I often criticize that also in TV gamma rays, by the way, the collaborations never really discussed their methods really well. These were always the papers that came later and that nobody wanted to publish quickly. But I think, yeah, we could learn a lot more from these methods, and they are so complicated now. Maybe it was not that complicated in the past, I don't know, and we didn't put enough emphasis on it. But yeah, I recently gave a talk actually at the company where I tried to describe a bit what we are doing in Magic with machine learning. And I tried to describe from the very basics how it works, just to get a fundamental understanding across to the people what this can do and can't do. Because a lot what I'm seeing is they react to buzzwords like deep learning and so on, and then they want to use that, but they don't have the understanding. So yes, outreach in the sense that we describe the methods that we are using in more detail for somebody who doesn't really understand it as not as a scientist. Yeah, I think it's very helpful.
But that really, just to continue this question, are people in companies really checking the, press releases from science like IC or whatever?
No, unfortunately they are not. I mean, obviously I am, and I'm going around. This is also one reason why the news is coming much slower. Like, for instance, AlphaZero that recently came out from Google, which was a big jump again in artificial intelligence. It arrived at Audi 1 week later or so. I mean, I had already discussed it with colleagues because I saw the news and I thought, wow, this is amazing. And then we go to a big talk in Audi, and the people there had just heard about it 1 week later, because it took a while to expand and reach the spheres. So
Continuing with the same topic, I think that the best way to channel these things is through the SPIA, in which in these meetings you have both people coming from institutes and from industries. We know well the SPIA meeting for implementation, probably it's not the best example, but there are other kind of meetings inside SPIA in which there is a close interaction with industry. It's probably the forum which is.
but what I'm trying to say is, with the awareness thing that I mentioned as the first step, is no one from the automotive industry will go to an astrophysical meeting or astrophysical instrumentation, because they don't realize that they're now using the same sensors. They just don't know it. And also there's always the feeling that they are the first to do this, like they are the first man on the moon. They don't know that they are not. So.
And this collaboration would be more like, okay, let's share information and maybe people, engineers or whatever, or you can really get, if the industry, for example, Audi is interested, you think you can get some that they invest in your.
I knew that you were gonna ask about funding. Yeah, I do think so. I mean, it happens. Like I mentioned, this collaboration we have now with the university there in Ingolstadt, more things like that happen. But so far has never happened with astrophysics, and I think it's sad. Why not? I mean, on the contrary, there's a lot to learn here. So I'm trying to push for that. I'm not influential enough yet, but I'm trying to raise awareness. Yeah.
Okay. Any other questions, comments? Okay. So thank you very much for the interesting talk, Karsten.
Thank you.